Hello everyone. As promised, I'm providing you with some screencasts to introduce and reinforce some of the concepts that were brought up on Monday, but we didn't have a chance to go through completely, or that were very rushed at the end of the hour. I've decided to back up and actually begin with the concept of the grammar and walk through the process of how we can use that grammar to build a parse table, how the parse table works, and then in the next presentation discuss the source code that actually implements a parser for the particular grammar we're looking at here. So let's jump in. To begin with, I'm going to work through the process of implementing a parser for the grammar shown here. This is just the example grammar that we've discussed in class a couple of times now. Basically a subset, a very small subset of the English language. So rather than trying to parse the language in its original form, there's a useful idea that we are using in the labs that can also be applied to this particular grammar, and that is, let's take advantage of the existence of a lexer. So you'll notice that I've highlighted the last kind of half of the grammar here, where we have productions that go from non-terminal symbols to the terminals that we would actually expect to see in sentences from this language, or from the language generated by this grammar. So a scanner, though not as powerful as a regular grammar, not capable of doing the same things, is very good at determining whether or not something is a symbol that belongs to the language, a terminal symbol, I should say. So the idea here is rather than needing to parse specifically the articles a and the, for instance, we can use the lexer or the scanner to first determine if those things are articles, and then just gather up a list of those. That's the same kind of concept we're using in the projects, where you are scanning through the text and determining what type of thing you're encountering, what kinds of tokens. And so in this case, we are simply going to use that same concept to identify tokens for articles, adjectives, nouns, verbs, and adverbs. The specific article isn't as important to us, as you'll notice that the rules in the top half of the grammar don't deal with them directly. Rather, they look at whether something contains an article or a noun, etc. So using the lexer, we can simplify the job of the parser. So that's what we'll do here. Now I'm going to go a step further, and for the sake of saving my wrist and saving space further on in the presentation, I'm also going to simplify the symbols. So instead of writing out sentence, we're just going to use an S, NP for noun phrase, VP for verb phrase, ART for article, ADJ for adjective, noun and verb are pretty obvious, and then ADV for adverb. Okay, so it's the same grammar. We have simply then eliminated the need for the original terminal symbols, the original words that we would be looking for in a text, by using a lexer, and so what's being fed into the parser will be just this set of symbols, and we've just renamed them. So with this being said, it's important to point out that in this particular grammar now, our terminals become adverb, verb, adjective, noun, and article, with our non-terminals still being sentence, noun phrase, verb phrase, X, and Y. There's also this lambda in this final production. We're going to need to do something with that lambda, so keep your eye on it, but for now we're not going to talk about it too much. Okay, so let's begin by building the parse table, which we can use to automate our thinking and use as a template for actually writing the source code for the parser. I introduced the idea of first sets on Monday, and so let's start by recreating those first sets for this particular grammar. Having introduced first sets, I'm hoping that you have a sense of where we're going, but just kind of to replant that seed, we can use our first sets to determine for a given non-terminal symbol what kinds of terminals on the input would be allowed if we were beginning to encounter such a symbol in the input stream. And remember that these non-terminals break up into multiple things. They break up into possibly several terminal symbols on the input stream. And so what our first sets are telling us is that if some set of symbols, terminal symbols on the input stream, could have been derived from a given non-terminal, our first sets indicate what we expect to see at the beginning. So for instance, if in a derivation of a sentence at some point this production or this set of productions was used, wherein we expand an X into either an adjective noun or a noun, then we would expect when we're encountering the terminals that came from this non-terminal in the input stream, that set of terminals is going to begin with an adjective or it's going to begin with a noun. So it's just a way of being able to predict how something was produced. If I'm not looking at an adjective or I'm not looking at a noun, then I'm not looking at the beginning of something that came from an X. Okay, so hopefully that made a little sense. If not, we'll hopefully solidify it as we go. So let's jump in here. Let's begin with the first set for the non-terminal symbol S. Now when we look at the grammar, we see that the first thing that shows up when we have an S, a sentence in this case, is going to be a noun phrase. So the first thing we see if we are dealing with a sentence is going to be a noun phrase. But of course a noun phrase is a non-terminal symbol, so we need to dig in deeper. If a noun phrase is the first thing that we see when we're looking at a sentence, well, what's the first thing we see when we're looking at a noun phrase? So we'll go on to the next production, specifically looking at noun phrases. The first noun phrase is an article. An article is a terminal in this grammar now, and so this will go into our first set for noun phrase, meaning that if I'm encountering a noun phrase in the input stream, then the beginning of that noun phrase will start with an article. With that knowledge, then, we can actually back up and say, okay, so the first set for the first set for S is equal to the first set of noun phrase, which is equal to the set that contains the terminal article. Okay, so this was just this recursive process we already looked at. Do the same thing for X, and we see that again, adjective, which is a terminal, is the first terminal to show up if we used this production, X to adjective noun, and noun is the first terminal that would show up if we used this production from X to a noun. So we end up with these two terminals in the first set. The first set for VP is simply a verb, and the first set for a Y is simply an adverb. Now again, there's this lambda hanging out here. So there's this what's known as a lambda production for the non-terminal Y, where Y could go to nothing. And we'll deal with this in a few minutes. Suffice it to say for now, our first sets don't really tell us what to do. If Y has been written as nothing, what's the first of nothing? Well, it's nothing. So I don't really know by looking at first sets and the input stream if I need to use that production in this situation or not. I need to know, because if I don't know whether to use the lambda production, it's impossible for me to determine if the input stream is valid or not without going further into the string and possibly needing to backtrack, which we're trying to remove from our predictive parser. So we'll come back to this lambda in a minute when we see where it actually becomes an issue. Okay, so let's build the parse table. The process of populating it is not complex, but we do need to understand the way the table is set up. So again, down the first column, or here on the left side, we've listed all the non-terminals in the grammar. So these are symbols that need to be expanded. Along the top of the table, we have listed the terminal symbols in the grammar. These are things that we expect to see in the input. So using these two pieces of information, a specific non-terminal that's on top of the stack, and some particular terminal symbol on the input stream, then we will decide which productions to use. And we will write these productions inside of the cells of this table and use kind of this row column format in order to determine which to use. Now you'll notice that there's a new terminal symbol that I've added to this table. So this $sign will basically serve as an end of file or end of input symbol. This will allow us to be able to actually know we're finished. And we talked about that briefly the other day, that we could either find it in the input stream or somewhere along the way have it inserted, but it's important to know that we've reached the end of the input stream. So we will explicitly indicate that in this case using the $sign. So that becomes something we'll deal with on the input. Okay, so let's see how we would go about this. If I can draw your attention down here to the grammar that I've got written along the bottom, we'll start with the start symbol itself. So if we encounter the symbol S on top of the stack, what can we do? What's available to us? Well, we can determine that by looking at the first set for S. And we see that it's an article. So what does this tell us? Well, it tells us that if there is an S on top of the stack, then the only symbol on the input stream that will successfully lead us, or rather provide us with opportunities for a successful derivation, in this case, is the set containing article. In other words, if I'm looking at S on top of the stack, I can look at the first set to know what symbols are even allowed on the input stream. In this case, it's just article. And that makes sense, right? For this grammar, a sentence has to start with a noun phrase, and a noun phrase has to start with an article. So if there's anything other than an article on the input stream, when we first begin, we can reject right now, because we know that we're not going to be able to find a successful derivation. Hopefully that made more sense. Okay, so looking at the first set for S, the non-terminal that we're actually dealing with, we can find out immediately which columns in the table for this particular row are actually going to contain productions. We don't need to have anything here for adjective, noun, verb, adverb, or even the $sign, because those things do not show up in the first set. Rather, we just expect that we will find some production that will expand S when there's an article on the input. Sure enough, we see that in this particular production here. And how do we know that that production will actually get us somewhere if there's an article on the input? We know by looking at the first set for the leftmost non-terminal on the right side of the production. In this case, there is only one production. And so we might go, well, obviously that's the one I'm going to use here. But that's not always going to be the case. For instance, down here for X, we'll see there are two productions, and we'll need to sort those out. But I'm going to walk through the process for each step just to pound it into our heads. So, we looked at the first set for S to determine which columns will actually have productions stored in them for the row for S. And then looking at the productions for S, we can determine which goes where by looking at the first set of the leftmost non-terminals on the right side of the productions. So the first set for noun phrase, article, and so we know that we can place this production in this cell. Okay? So you'll notice that we're only writing the right side of the production. The left side is indicated already by the row that we're writing the production in, and by its identifying symbol. Okay, so we've dealt with S. Let's change color and look at some of the others. So for a noun phrase, so now we're going to work on this row. If we look at the first set for noun phrase, we see that again, it's article. So we expect, and that's the only symbol, so we expect that we will have a production that we can place in this column on the row for noun phrase. Looking at the productions available for noun phrase, there's only one, but let's go ahead and double check that we know where to put it. We look at the first symbol on the right side of the production, and we see that it's article. Article is a terminal symbol. The first set for a terminal symbol is obviously just the terminal itself, so we know that this particular production would belong in the row, in the column indicated by article, and so we'll go ahead and write it there, article X. Okay, and that one's taken care of. Let's change colors again. We're now going to deal with the non-terminal X. Looking at the first set for X, we see that both adjective and noun show up in that set. So I know that there will be a production that I can invoke when I see an adjective on the input stream, and there will also be a production that I can invoke when I see a noun on the input stream. So now let's sort them out. If I go to the productions for X, I see again these two, adjective, noun, and noun. Let's look first at noun. So the first set for noun is simply noun. So the production that converts an X or rewrites an X as a noun will be invoked when I see a noun on the input stream and an X on the stack. So that's this position right here. Okay, looking at the next available production, the first symbol is an adjective. First of a terminal is the terminal, so the first of adjective is adjective. So when I see adjective on the input, then I can use this rule. And so that sorts those out. Now that was kind of a trivial example, but hopefully you can see how that process could be used to sort out any number of available rules, as long as we don't have two that begin with the same set of first, or the same, in some sense, the same non-terminals, or the same terminals or non-terminals. In other words, as long as there's not ambiguity, if there's not multiple rules that could be used. If there is ambiguity, then as discussed in class, we know that we have to somehow clean that up. And we'll actually discuss that in class shortly. Okay, moving on. Let's now look at verb phrase. So the first of verb phrase is verb. So we expect to find a production that we can put here. Looking at the available productions, there's only one, and sure enough, it begins with a verb. So I'm going to go a little faster here, assuming you have the idea. That's the only rule available there. So now we'll look at Y. Now Y has two productions. We see that when we look at the first set, it only has this one element in the in the first set, adverb. So we know that we're going to have a production sitting here on the table, but that's only going to be one of these two. We can immediately see that it's this one. But what happens with this lambda? Well, let's discuss that in just a moment. So here are the guts of our table. We have most of the productions in place. Before I move on and talk about the lambda, I do want to bring out an important point. The productions available when we see an S only expand us to a noun phrase followed by a verb phrase, and both of those are non-terminals. But you'll notice that noun phrase expands to something that begins with an article. X expands in both cases to symbols that are all non-terminals. Are all terminals. I always get my tongue tied around those words. And verb phrase expands to a verb, Y to an adverb. So when we use a production that expands to something that has a terminal as the leftmost symbol, we're going to end up with that terminal on top of the stack. And I should point out here that when that happens in the process of parsing, we cannot expand those terminals any further. We don't need to. The minute a terminal shows up on the top of the stack, we would be trying to match that terminal with the input string. Specifically with the current symbol on the input string that we're looking at. If it matches, then we'll both mark it on the input stream or toss it aside, however you want to think about it, and also pop it off of the stack, uncovering the next symbol. So every time there is a terminal on top of the stack, we're attempting to match it. If at any point it fails to match the input, something has gone wrong, and we would reject. If we're able to match these terminals as we go, all the way down to the stack symbol on the bottom of the stack, then we know we've successfully parsed the string and we would accept. Okay? And again, we'll look at that closer in a moment. So here's the table finished, or rather almost finished. We still have this issue right here. Why, or excuse me, how do I know what to do with this lambda? I've already given us a hint. Got ahead of myself a little bit. There should be a production here. But the question is, how do I know that? The way we're going to know this is by looking at something known as follow sets. I can't look at a first set when dealing with a lambda production to determine where to use it because there isn't anything there. But you'll notice that if a particular non-terminal shows up in a derivation, either it's going to be at the very end of the string or it's going to be somewhere in the middle. In other words, either there will be another symbol that follows it or the end of the string will follow it. For each symbol in these productions, in reality, we can talk about what comes after it. For instance, if I see a noun phrase, it's going to be followed immediately by a verb phrase. I know that because noun phrase only shows up in one place on the right side of these productions. And a verb phrase must then follow the noun phrase. So, in other words, the first thing I will see after a noun phrase is going to be the first part of a verb phrase. A verb phrase follows noun phrase. We can look at other things. An article. Okay, what follows an article? Well, an X follows an article. I know that because article only shows up in one place in the grammar, on the right side of the productions. So when we start talking about things that follow, instead of first sets, we talk about follow sets. Okay, so let's construct follow sets real quickly here. We'll begin with the follow set for S. Now this is our start symbol. And there is a universal rule we'll apply here that whenever we're computing the follow sets for the start symbol, it will always include the end of line symbol or the end of input symbol. In this case, we're using the $sign. And if you think about it, that should make sense. If S is the top level symbol, maybe it represents a program, maybe it just represents a sentence in English, etc. If it's the top level symbol, then what comes after it? Well, nothing. It's the end of the input. Unless there's some kind of recursion going on or iteration going on, in which case there might be something else. But ultimately, where does the input stop? It has to stop once we've finished one of these top-level symbols. Okay? So we know that the follow symbol, let me try this again. We know that the follow set, at the very least, must contain this $sign symbol. So we'll add that to our follow set right now. Now it turns out that there is no recursion on the non-terminal S. So this is the complete follow set for S. Okay? Now let's look at the follow set for a noun phrase. If I look at the productions for the grammar and I find noun phrase, I find that the only time it shows up, it's followed immediately by a verb phrase, which is a non-terminal. So the follow set for noun phrase is going to be the first set for verb phrase. If I look at verb phrase, I see that that's a verb. So I can go ahead and write this. Now, that makes sense if you think about it, right? What should come after a noun phrase? A verb. If I've seen a noun phrase on the input and I've successfully pulled those pieces of the noun phrase together, the next thing I expect to see in the input stream, if it is a valid sentence, is a verb phrase. And the first thing I would see in a verb phrase is a verb. So the follow of noun phrase is verb. Or the set containing verb, I should say. Follow set of X. This gets a little bit fishy, so we need to think through this. The only time X shows up, it shows up on the tail end, or the rightmost side of the right side of the production. There's nothing behind it. Well, there kind of is. The X shows up on the right side of a noun phrase. All of this is a noun phrase. So what follows X? Well, whatever follows a noun phrase follows X. So it turns out that the follow of X is the follow of noun phrase. So it becomes the set containing verb as well. Okay. Moving on, follow of a verb phrase. If we look for verb phrase in the grammar, I'm going to clean this up a little bit over here. Again, we see verb phrase only shows up in one place, and it's on the tail end of this particular production. So, does it have anything following it? Well, yes. If I look at this entire piece as symbol S, because it is, then the follow of verb phrase is the follow of S, or at least it contains the follow of S. If verb phrase showed up in multiple places, it may have other things in it, but at the very least, we can see that it's going to contain the follow of S. The follow of S we already determined to be simply the $sign. Okay? And then finally, we want the follow set for Y. Y shows up in one place in the grammar as well, on the tail end of a verb phrase. So the follow of Y is going to be the follow of verb phrase, or it's going to contain it at the very least. So we'll go ahead and write that set. Again, if Y showed up somewhere else, maybe in front of some other non-terminal or terminal on the right side of the productions, then there may be other things in the follow set as well. In this case, Y only showed up in one place, so we end up with this pretty simple set. So the follow of Y then is this $sign. Why do we care about all of these follows? We care about them in the context of the lambda production. If at any point we're trying to expand to Y and we don't see an adverb on the input, then we know that we can't apply this particular production. But how do we know if we can apply this one? Well, we would know by looking at the follow set for this particular non-terminal. And if the next symbol on the input belongs to the follow set, that tells us we can successfully use the lambda production and move on. It indicates that the next non-terminal in the stack should be able to process that terminal on the input successfully, and we'll be able to keep going. So, when looking at a lambda production, instead of first sets, we look at follow sets. So the follow set for Y includes the $sign. So we would expect then to be able to insert this lambda production somewhere in the table. And sure enough, we can insert it here, where if we have a Y on the stack and a $sign on the input, we know we can invoke this production, the lambda production. Okay, so that finishes our table, and this is what we end up with. Now I wanted to demonstrate actually using this table. Using it is pretty straightforward, it's pretty easy, but before we use this example, I need to kind of finish this slide up a little bit. I failed to include the terminal symbols here at the end of these sentences, and I want to draw your attention again to the presence of terminal symbols, article, adjective, noun, verb, and adverb in the table. So let's try to parse this. We'll begin by building ourselves a stack over here, and I'm going to use this symbol to indicate the bottom of the stack. And we'll begin with the start symbol S on the stack. We'll parse this sentence first. So we will begin by looking at the first symbol, article. We're looking ahead, if you will, at that one symbol, and try to parse this. So I have an S on the stack and article on the input stream. So that tells me that I can use the noun phrase, verb phrase production right here. So I will do that by expanding the symbol S on the stack to the symbols noun phrase followed by verb phrase. Okay? Now you'll notice we didn't yet match anything on the input, so we stay in the same place. We're still looking at article on the input. So now I have a noun phrase on the stack and article on the input. This tells me that I can use this production to expand noun phrase on the stack. So I will do that. I will rewrite noun phrase as an article followed by X. I now have a terminal on top of the stack, so I need to try to match it. Sure enough, article on the stack matches article on the input string, so I will pop article off of the stack and I will move past the symbol article on the input. I'm now looking at a noun on the input string and an X on the stack. So let's clean this up a little bit. So I have an X on the stack and a noun on the input. This points me to the production that expands the symbol X to a noun. So you see we've been able to completely disambiguate what to do there. So we'll go ahead and apply this rule by rewriting X as a noun. I now have a terminal on the stack, so I check to see, and sure enough it matches the terminal symbol on the input string. So I can mark that as matched and pop this off the stack. I now have, let's clean this up a little again. Go ahead and get rid of all this, just so it's not a distraction. Okay, I now have a verb phrase on the stack and a verb, okay, on the input. So I know I can apply this production. So I'll rewrite verb phrase on the stack, pop off verb phrase I should say, and write verb followed by Y. Verb is a terminal. It happily matches what I have on the input string. So I'll pop it off the stack. Mark verb is utilized. And again, we'll clean up after ourselves. Okay, so now I have a Y on the stack and a $sign on the input symbol. And so this is where our lambda production came in handy. I know that I can successfully apply the lambda production, which means I pop the Y off the stack and I do nothing. Okay, at this point I have the end of file character on my input and an empty stack. And that's what I'm looking for to know that I have a successful derivation. And so I know that I can accept that particular string. We had success. Okay, let's look at another example. In this case, we're going to try to parse this sentence, which is article, adjective, noun, verb, noun. Now we know it's going to fail because we understand the grammar, but let's walk through the process of seeing how the machine would determine that it has failed. Again, we have to add this $ symbol at the end. So we'll recreate our stack, place an S on the top, and I'm going to work through this rather quickly. So I have an article on the input, and I have S on the stack, so I'll use noun phrase, verb phrase. I now have a noun phrase on the stack and still an article on the input. So I can use the article X expansion on noun phrase. Production, I should say. I've got an article on the input and an article on the stack. So I'll pop off the article and we'll move on to the next symbol. I now have an X on the stack and an adjective excuse me, on the input. So I will use this production to rewrite X as adjective noun. At this point I can match adjective with adjective, so we'll do that. Okay. I now have a noun on the input. I also have a noun on the top of the stack, so those will match. And now I'm looking at a verb phrase on the top of the stack and a verb on the input. So I'll rewrite a verb phrase as verb followed by y. I have a terminal. It does indeed match, so we can go ahead and get rid of it. Move on to the next thing. So I now have a y on top of the stack, and I have a noun on the input. Let me change colors. That's not very easy to see. So I have a noun on the input and a y on the stack. You'll notice there is no rule here. There's no production. This is indicative of the fact that this is an invalid string. I have no way to create this string using this grammar. So at this point, I can reject with a y on the stack and a noun on the input string. And we're done because we've rejected. Okay, so that's how we build the table. That's how we use it. Now comes the question, how can I actually implement such a table in code? And of course there are different ways. We're going to use recursion to build this particular parser, and I will walk through that process in the next presentation. So I'll see you then.